this rectangular is the process. With the process, what we are doing, we are putting the PID. It will be a little bit problematic since I'm not using the, maybe wait a moment and I will use a mouse. I will get a mouse. Okay, I have my mouse. It will be much more easier for me to do anything to draw. Okay, so we have the PID. With the process, I was talking to you that we have something which is called FD, file descriptor. And normally we have the file descriptor 0, 1, and 2. 0, this is the standard input. 1 is this is the standard output, and this is the standard output error. So everything which is written in the red in the console, this is the thing which is happening here. And with that file descriptors, these are the handles to the things that can be the files, that can be the terminals, that can be the devices like the monitor, and so on and so on. Basically, in the Linux, in the POSIX, everything is a file. So this is very important thing. And this is placed here. So operating system is giving you all that things. Operating system, as you ask for, it can give you all the other file descriptors. For example, the inputs to other processors or something like that. But this is the other thing. So we have the PID. We'll be getting some kind of the memory. Okay, so mem. Yeah, and so on and so on. So basically, this is what we are having here, and in here we have all that things accessed and gained, but we are waiting for the CPU time. This is the only thing which is really needed here. So whenever the scheduler says, okay, this is your time, it is giving the scheduler come to us and says you have to be suspended right now. He's moving us from the running to the waiting state once again. So this waiting state is equal to that thing that we do not have the CPU time. And there is also the possibility to be blocked by the other process, or blocked due to the fact that we do not have the resources. And through the blocked, we can go to the waiting and to the running. So to the running, we can go only one way, through the waiting state. In the waiting state means that we have everything, but we do not have the CPU time. And we can be in the main memory, and we can be also, whenever it looks from the perspective of the operating system, that it was a long time we haven't been executed. We can be just moved to the swap page space or the page file, and then we can stay here for our resources for our CPU time. So basically, it is some kind of the mechanism in which our process is trying to make a cleaning of the memory, because, for example, we are getting to that state, we will not be having much memory in our operating system. Yeah, so this is it. Sorry, maybe I will just make it clear. Yeah, so once again, about the thread, this is the kind of the chunk of binary, so individual function, small element of our process that can be run in some process, and we can have the several threads. They will be running in parallel. They have the private registers, private stack, common code, common data, common files. So as you can see, there are some common things, there are some private things. About the common data, this is, for example, the global data. And all threads within a process share the same address space. It means that basically they're using the address space of the process. Threads in the same process share process instructions, so the code, most of the data, not everything. File descriptors, signals and signals handlers, and other things. Maybe we do not focus here too much. But how it's going to happen here? So basically, we have the application on our disk. Okay, that application has a kind of the instructions, and the instructions are being loaded from our disk to our RAM by our operating system. So there will be instantiation of that instruction of that operations. Sorry for a moment. In the RAM, this is the thing which is very physical. Okay, we have the individual chips and so on. From the perspective of the operating system, for example, the Windows or the Linux, we don't care in which chip will be having our application. This is realized through the idea of the virtual memory. So it means that operating system is also putting some kind of the abstraction of the hardware aspect of the memory or allocation of the individual memory addresses in the in physical devices. And it means that in our RAM, we can have the process 1, the process 2, process 3, M, and so on. As you can see, there are threads, that little box here are the threads. And what we are getting, the scheduler is managing all that queue of the threads in that way that it takes the priorities, it takes some kind of the information about the time, and gives you possibility passage to the CPU to be executed. And there is something which is called the context switch. I was talking before about it. So context switch means that basically we just, the context, this is the thing we call the actually, let's say, executed piece or scope of the instructions. Maybe will be the nice definition. So basically, when we are talking about the context switch, it means that we were previously executing one piece of the code, and currently we have changed it to be executing another piece of the code, but totally different of the code. And from the perspective of the thread, so when we are talking about in the thread, as you remember, the threads has different stacks, they may have the same instructions, but for example, the different variables. And it means that whenever we are making the context switch, and previously we were executing the thread number 1, and we are, let's say, trying to change it to for example, thread number 2, it means that we have all that things saved on our stack, as well as the place in which we have been suspended regarding the realization of the thread 1. So this is that thing I was talking, which is very costly from the perspective of the operating system. So many context switches are costly through the perspective of that saving and returning to the state in which we were suspended. So we have to do it in that way that there will be no frequent context switches, because once again they are very costly from the perspective of the operating system. About the process, maybe I will be talking it later, because as far as I remember, the lists we are talking right now. Let's go here, and currently we'll be doing this list. This is also more about the processes, about the threads. So I will focus more on the threads right now. So I will be talking about the process and process creation and other things later. About the thread creation. The thread creation, this is the thing which is from the perspective of that one single thread in our process. This is done by the operating system. It's quite easy. From the perspective of when we want to manage the process, the thread creation, we have to use the function which is called the pthread create. It is placed in the pthread.h. I'm talking about the POSIX standard, yeah. So basically, whenever it will be applicable to all the links to the other systems that are confirming the POSIX standard. Okay, the pthread create. This is the function which is having several arguments uh, like the thread ID, the attributes of the threads, the function it will be realized, and the arguments will be passed to that function. As you can see, this is a very big number of the pointers. And what is more, these are the pointers which are the void pointers, so you can pass anything there. This is a kind of the advantage and the disadvantage, because in order to make it good way, you have to really be sure what you are passing. So basically, uh, you can pass uh, to your function, which will be realized by the thread. For example, the I don't know data structures of the strings or something like that. But you have to be aware of that all aspects of that. So basically, you first of all in that thread creation function have to somehow decode what you have inside that, for example, void pointer argument. Okay, and here we have the example. So we created the print message function, and in the print message function, which has the such interface. This is the void to the pointer. Okay, this is the pointer to the void. Frankly speaking, it's getting some kind of the another pointer. We are creating pthread t as a kind of the object. And this is the thing in which we are coming to that kernel and to that objects of the kernel. Let's go here. Yeah, to that objects. So pthread t, this is the object, and the service, this is the pthread create, for example. So let's get back. So we are creating, for example, here 2 threads. I mean that the structures, okay, because these will be not functioning threads right now. With that threads, we have to create, first of all, this is the handles. These are the handles to the thread. These here I'm putting the node because I don't want to have special attributes to pthread. You can read about the attributes, what's inside. If you want to get some kind of the information what is about, for example, pthread h, if you put something like that, you can get easily here. And for example, you have here create the function you can go into, and you can read what's inside and what kind of the errors. This is very important because every function in the C, and especially whenever we are talking about the kernel functions, it is returning some kind of the ints, and ints are used as a kind of the error codes. Whenever this is successful, we are getting the 0. Whenever it's not 0, it means we are getting some kind of error we can check. And about the RT, we can try to check, and it is not written here what is inside. And frankly speaking, I do not remember what's inside, but these are the attributes for the thread. And we can try to check. Thread attributes object pointed by which attribute values, blah blah blah, and we can say, yeah, you can frankly speaking try to check what's inside, because I totally don't know right now, and normally I'm not using it, but it's not very important. In a frequent way, or frequently you will get or see the null here. So we are not pushing anything special to that thread creation function here. The third argument, this is that message function we are passing, so that pointer to that message function, and we are passing also pointer to the message. And this is the very important thing, pthread join, because imagine right now we have the threads, okay? So basically we are here, we started the application here, and we go here, we take, this is that pthread create function here, And it means that we had our original thread, and we have additional new threads here. And imagine that this our uh, normal original should end somewhere there. I don't know, after 30 minutes. There is one thread which is ending here, another thread is ending here, another thread is ending here. From the perspective of the operating system, when our operating system gets information that any of the threads is just finishing or finished, it kills the application. So the applications will be killed, application will be killed here. So basically, that execution will be not done, that execution will be not done, that execution will be not done. Basically, all that executions might be very important from the perspective of the functionality, but from the perspective of the rules, it will be not executed due to the fact that we're killing the application here or ending the application here. So the pthread join will give us the possibility not to have such situation, but to move and wait to all the threads to be ended here. Uh, Sorry for a moment. Please give me 5 minutes and I will be back. So 5 minute break. 5 minutes has left. So yeah, this is very important about the join. As I said, whenever you do not put the join, you will be observing very strange situations with your threads and execution of your code, that you will be getting the different results and so on. Okay, maybe clear. Yeah, and here comes the problem we want to talk about. The problem that whenever we are having the several threads, and we'll go maybe a drawing here. Imagine we have the something like this is the nice example I'm using all over the time. We have the ATM, so we want to get the money from the machine. And imagine we are doing it in the same time, twice or more time. And imagine the thing which is happening is all the request starts from get the balance. Okay, maybe I sorry, get the balance. This is the first stage. Maybe I will, because it will be better to do it that way. And make it a little here. Yeah, get the balance. And balance minus y withdrawal, and it will be new balance. Okay, third point, save new balance. Yeah, and this is what we are having here, and this is quite intuitive that it should work. Okay, because we are getting the balance, we have to get now how much time, how much money we are just getting out of the ATM, and we have to make the update of the value of the balance in our account. But whenever we are doing it in the same time in the two places on the from the perspective of the two places, or the perspective of the two threads, we are having that situation that both threads, both requests are asking about the balance in the same time, and both of them are making that subtraction, and both of them are trying to save the value. And imagine right now that both of them are asking about the balance in the same time. Both of them are from the balance, for example, $2,000 are subtracting $200, and both of them are writing to the actual value of the balance 1800s. So basically, for that given thread, every thread was okay. So from every thread was doing well. So from the perspective, what was not, all of the threads in the, let's say, uh, each thread is working properly. Each thread is doing the right job, but together they are messing everything up. So basically, due to the fact that there is no such way that we are waiting for the first thread to let's say change the new balance or the saving the new balance, we are having that problem that we are not we cannot see that second operation is happening or the results of the second operation is happening in the same time. Okay, this is the kind of the thing, frankly speaking, which is associated with the bad design of this operation, because this is normally not that way. We are not getting the balance, we are only sending the balance withdrawal, and that one element which is let's say executing the request one by one is making that operations, and through that design we do not have the possibility to have two operations done in the same moment. But this is, frankly speaking, what is happening in the multi-threaded operations whenever we are writing anything to the whole to the one variable. And I will show you a code here. Sorry, clear. Let's go there to the code. And there is that code which is called producers, I think. Yeah, and this is the basically the thing I'm talking the things I'm talking about. These are the very old things. These are the things that haven't changed a lot from the perspective of the years. And frankly speaking, this code has been, as you can see, in the 2005 written. But basically, the idea about the multi-threading and the race conditions, because this is what we are observing, and other things, these are the things which are known, I don't know, from the 80s or something like that. And here we have the application, which is making the dot product of two vectors. And that two vectors are the vectors of the length 100,000 of the elements. So from the perspective of the operation, when we have the multi-core system, it is some kind of the performance, not good idea about the performance to do it one by one. We can just make it in the parallel. For example, we can divide our vector into sub-vectors and individually treat them. And this is what that function is, frankly speaking, or that application is, frankly speaking, doing. It is dividing the whole length of the vector to the 8 chunks, and it creates the 8 threads, and individual threads are processing the individual chunks of that vector. And in the end, we should have a nice vector, which is nice dot product of two vectors. Yeah, I will not go too much into the details, but frankly speaking, what we are doing here, we are making some kind of the settings, but in the end, we are making the summation and the sum. This is the global variable here. Also, the global variables are the a, b, and b. These are the vectors, but we don't care about them because we want to get the sum of the dot products, okay? And as you can see, this is the global variable, so it is being shared by the different threads. And this is the situation or the moment in which we have problems regarding all the threads. So all the threads are trying to write something to the sum, taking on the actual value of the sum inside and make it a little bit updated. When we go later, we can see there are different other things. These are the pthread create written in the loop. This is the common thing, and the joining also in the loop. So we are waiting all the threads for the final result to be ended. So basically, not very special thing happening here. But if you go GCC producers, okay, I'm getting the error because I have to add the LP thread library. Okay, and now if I run, as you can see, I have the global sum 272,061. Basically, I should get some kind of the 800,000 because we have the 100 of the 100 elements of the vectors, and we should get some kind of that value. But the more problematic thing is that from time to time, that value from each iteration, the value is changing, as you can see. Even the difference here is 100,000. So this is the thing which is not very static. It is dynamically changing, and this is the thing which is showing that we have some kind of the error. Basically, in the operating system, if you have such thing that, or maybe in your application, if you see that you have not deterministic results, it means that you have some kind of the timing problems with your functions. And the race condition, this is the kind of the thing which can we express as a kind of the timing problem. Because frankly speaking, the point of the synchronization between the threads is not constant, or there is no such point of the synchronization. So this is why we have such problem. And the reason, or let's say the thing we can perform here is put the mutex. So mutex, this is the thing which is making the critical section synchronization. Critical section, this is the piece of the code which is creating our problem, and frankly speaking, this is the critical section here. So if we put the mutex here, just somewhere here, we'll be getting rid of the problem, and we'll be doing it in the moment. What we have to do, maybe I will do it in that way that, because it will be, I do not remember never what to write. So first of all, we have to define something like the mutex p thread mutex t mutex 1 equals to p thread mutex initializer. So what I have done, I have created the global variable. It has to be global, but it is somehow this is the safe global variable. I will show in a moment how it is being constructed. That the mutex, it will be accessible through all the threads, okay? And I'm making the initialization of that mutex. And what I have to do here, I have to go to that critical section. I have to get them some braces because there was no braces before. And I have to do p thread mutex log. So basically, about the mutex, mutex can be locked or unlocked. These are the two stages in which it can be. And we have putting here the handle to the mutex. And whenever we made a change, we can make the unlock. Let's go with the compilation. Yeah, it's working. And you can see right now global sum is equal to that value. Nothing more. Yeah. So frankly speaking, only putting such thing has, let's say, fixed our problem. And currently we do not observe something like the race condition whenever that the last thread that will be writing the value to the actual value to the value will be having the right the supremacy under against the other threads, because the last thread will be writing the answer, will be that answer visible for us, but because other will be just vanishing due to the fact that that one last thread is writing something to us. So this is the race condition. So the race condition is whenever the threads are trying to modify the variable, which is somehow they've shared, and all of them tries to do it in the same moment. And from that perspective, we cannot see all the changes because some of the changes are overwritten by the other changes. Of course, there is a disadvantage because we lost some kind of a performance here, because this is the point in which our threads will be stopping for a moment and waiting, for example, whenever it will be ready for them to be, let's say, writing something or not. Maybe that performance dropping is not so big. For sure, it is better to have a good results than the fast and bad results. So this is the that thing. Unfortunately, I cannot show you how to measure. Maybe on the next lecture, I will be showing how to measure what would be the performance drop regarding the mutex. About the thing about the mutex, let's go. Maybe I have that definition here in the presentation. Uh, sorry here. So what's inside the mutex? Mutex is a union, so something like the structure, but in that way that in the structure we have the specialized places, and all of the places are in the same time visible in the union. All that elements can use the whole memory of the union, and the memory is equal to the memory of the biggest elements, basically for that struct. So there can be a struct, there can be a car, there can be log int, but none of them together. And inside the struct that pthread mutex s, if we go deeper, we can see that there is something like the log information. There is the count, how many times probably it has been locked, and the owner. And this is the most important thing from the perspective of our application. Whenever we are locking the mutex, we are checking first of all what is the state. Whenever the state is locked, it means that we have to check who is the owner. Whenever we are the owners, I mean that my thread, my ID of the thread is the owner, I can do the change in that variable. Whenever I'm not the owner, I have to wait for the possibility to be locking that mutex, and there will be a queue of the queue of the threads waiting for that possibility to lock the mutex. So this is, frankly speaking, what is happening under the hood of the mutex. And this is the reason why the mutex is the synchronization point here. There is one important thing regarding the mutexes, because mutexes has several maybe disadvantages or the problems here. And here we have the priority inversion problem. We have the three threads, low, middle, and high regarding the priority. We mean that the high priority means that that thread should be executed before all other threads, and whenever other threads will be executed, we just should suspend and preempt that other threads and take the time for that high priority task, high priority thread. And here, 8 is waiting for a unit from a semaphore or the mutex, and it is getting. So it is being executed here, okay? Here, B wakes up and preempts the thread A. So basically, it means that from this time, we are moving the thread A to the waiting, to the ready state, but it is not operating, and the B is being operated. But the thread A has used some kind of the semaphore, some kind of the resource. I mean, it has locked a mutex, for example. Then another thread is going to rise up, and C wakes up. It is high priority task. So basically, it swaps the B to the ready state, and it is being executed. But it gets to the point when he wants to get the resource that it is being used by A, and A hasn't released it because it is in the ready state. And in this moment, C cannot continue, so it is going to sleep, while B, the middle priority task, is being executed, and A is still sleeping or still ready, maybe not sleeping. It is waiting for the time of the CPU, but it is not getting because the B is still getting that time. And in this situation, this is the priority inversion because the high priority task cannot be executed due to the fact that it is waiting for the resource that has been locked by the thread that has the lowest here the priority, but that thread cannot release that resource due to the fact that higher priority task, but not the highest priority task, has that resource, has that time, and cannot give the time back to the A. And from the perspective of the B, it cannot be preempted because the C is not ready to be ready, and A has a low priority task than the B. So basically here we have the stack in our situation. Uh, so we have to do something in our system. So we have to kick a little bit our threads and that kicking is called the priority inversion. For a single moment, or let's say for a limited number of time, we can increase the priority of the thread A to be a little bit bigger than the B, for example, in order to release that resource and to continue the work of the C. So this is what it is called the priority inversion, and this is very important thing from the perspective of the mutexes. And about the priorities, normally we are putting the priorities with the numbers, and this is the typical thing. We are not making the number one by one. So I mean that priority number 1, 2, 3, 4, but rather 2, 4, 6, and so on, just to make it possible, for example, from the priority 2, here was the priority 4, to make it 5, but not greater than the 6 for the sake of this example, for that priority of the task C. Yeah. So this is the moment I want to suspend. I just want to ask whether do you have any questions? Maybe I will later, let's say, record some kind of the talking about the project list, just to tell you about the things inside the tasks. But now, if you do not have the questions, please look into the chat. I posted there the link to the short test. Please execute it. And as I said on the very beginning, right now I'm stopping sharing and I'm stopping talking. And yeah, whenever there will be any issues, I will be ready after hour and a half, something like that. So close to the noon, I will be answering all the questions whenever something will arise. Whenever the recording will be ready, I will be also sharing it on our Teams channel. Okay, so thank you very much for being today. Thank you very much for making me possible to make it on the starting from the 9 o'clock. Yeah, have a nice day. Wish you luck regarding the short test, but I think this is rather the easy thing. As I said, one thing about the short test, please remember, you do not have to write it now. You can do it, for example, tomorrow, later this day, or something like that. There is only the limitations about the number of time you need for writing the short test. It will be 12 minutes, nothing more. There is no time slot for that special. Okay, so thank you very much once again. And
Excuse me, I have
yeah.
a question regarding the test. So, is it possible to retake the test if you're not satisfied with your performance?
Retaking the test, not really. Whenever you will be having some kind of the problems with the communication, please write to me. Okay, I will check what happened and so on and so on. For example, you have some kind of the internet dropouts or you are not able to finish, but this is the rather the thing that if you start the test, you have to write it and there is no retake.
Okay, thank you.
But never, once again, you do not have to write it now. You just can wait for the recording of this session to be published. Then let's say read hear the recording and write the test, for example, on the Saturday, Sunday, whenever you want. Okay, so I'm stopping the sharing. Thank you very much. Have a nice day. Bye.
Thank you. Goodbye.
Thank you. Goodbye.